Okay, so thank you guys that came up and gave me my quick sketches here. Now, this one you did for 3 months last year. We reviewed all last unit, right? These bottom two are probably some of your first experiences with graphing things with bigger exponents than just a quadratic like a 2. But what we're going to figure out today is we're going to use all these things. I feel like I've been telling you guys this for 2 weeks, right? The reason why I really need you to know your quadratics is because we're going to see that a lot of the patterns that worked in quadratics apply to higher degree polynomials. Does anyone remember what a polynomial is and can remind the class? What's a polynomial? Here.
An equation that has multiple, I don't remember what the word is, but the different sections.
It's an equation with different sections. Awesome. The sections are called terms, but it's things being grouped together with multiplication and then either added or subtracted. Perfect. Does that make sense? So in secondary 1, you spent most of your year on linear polynomials, y equals mx plus b. Last year, you spent most of your year on quadratic polynomials. Okay, on quadratic polynomials, so x squared. So to this unit, we're going to start realizing how x cubes, x to the fourth, and things like that relate, okay? Now, when we did our parabola here, how are the factors related to the x-intercepts? What, can someone raise their hand and tell me what they got for that? How are the factors related to the x-intercepts? You already drew one today. I want a new voice. Yeah. Sam.
Oh, the factors are like...
Or Tim, I can't remember.
The x-intercepts.
Okay, so the factors represent the x-intercepts. Exactly the same? That's opposite sign, right? It's the 0. It's what makes it 0. Okay, so here, my factors were the x plus 3 and the x minus 2, but my x-intercepts were here. Pause. Most of the reason why many of you got quizzes wrong on Canvas for Unit 1, like, I don't know if you saw, but like on every question, I wrote in all caps, notation, notation, notation. That was me trying to hint at you to watch your notation. So an x-intercept is a coordinate point, right? You have to write it out like a coordinate point, okay? So keep that in mind if you give me tickets to open up any of the assignments that closed yesterday, okay? Anyway, here I have, how are the factors related? Well, the factors give me the x-intercepts, right? It's the zeros of those x-intercepts. That's why you make it positive or negative. You switch the sign. Now, I want you to look at your graph on 2 and 3. Do you think that pattern that held true for quadratics holds true for bigger degree polynomials? What do you think? Did that hold true? Look at your sketches.
Can you re-say the question?
Sure. Hold on. This is going to be a long day unless we perk up a little bit here, you guys. It's an easy lesson compared to what you've been doing. Are you with me? We're awake? Okay. So my question was, for about the 5th time, but now we'll all listen. Does the pattern of how these factors represent x-intercepts hold true for numbers 2 and 3? You think so? Now remember, these were just quick sketches, right? So you'll probably want to use the ones on your paper exactly. Was the x-intercepts on this one 2, 0 and negative 2, 0?
No.
Yes, they should have been.
My bad. I did a -3 on accident.
That's okay. I said quick sketch. Okay. And then what about on this one? Did the pattern still hold true? That will always be true. It doesn't matter. That's one of the reasons why knowing how to factor quadratics is so important, is because factoring quadratics will help us learn how to factor x cubes, x to the fourths, x to the fifths. And something in factored form will always give us the x-intercepts, okay? So that's what we're doing today is we're going to start looking for patterns of things we learned on quadratics and see how those patterns relate to graphing x cubed, x to the fourth, and so on. But there's going to be a lot of little pattern questions. So I need you to be actively involved in this lesson or it's going to be a little painful. Okay?
Okay.
Look, some of the people are showing me. Are we ready? We can do this? We're going to perk up? Okay, I got a few more head nods there. Maybe I should just randomly call on people today for answers?
Ooh, that sounds cool.
No? Well,
Yes.
prove me I don't need to, or I will. Okay? Now, let's talk about the new thing. The new thing. How many times has the curve changed direction? That's not something you've probably talked about before, but I thought you might be able to figure it out. What do you think a direction change means? Can someone I haven't heard from yet today tell me what you think a direction change means?
Changing if it's going up or down.
Perfect. Changing if it's going up or down. Okay? This graph here is concave up. So when she's saying the graph is going up or down, that's not talking about concave up, concave down. That's a different kind of up and down. Does anyone remember the vocab words from last year for that? It's okay. Increasing and decreasing. Increasing and decreasing. But that's good. So how many times did you think this one changed its direction?
Once.
Once is correct. What was our vocab word last year for that point where it changes direction? Vertex. Yes, good. Okay, now let's look at this one, which is a cubic. I know that because look, 1, 2, 3 x's, right? How many times does this graph change direction?
Three times. I just said that because of your face.
I've heard twice and 3 times. Twice.
I only said 3 because you didn't write it down.
Right here. And right here. Up, down, up. Right? But there's only 2 places where it's changed direction. You with me?
Yes, ma'am.
Those are still called vertices or vertex, right? But they're also, we have a new word that represents the same thing now. It's called a turning point. So what you think of as, oh, come on. What you think of as vertex, we have a new vocab word we're going to start using interchangeably called turning points. This is going to be a long year here. Okay, okay, here we go. Ah, hooray. Okay, I can't. Okay. Wait for it. Sorry, video. Technical difficulties. But we're winning. We're winning. Fine? Is that fine? Hooray. Okay. Now, how many turning points does this one have? 1. Look, this one here, it kind of like came up, but isn't this increasing still that whole time? It just kind of flattens out for a second, right? So this one only had 1 turning point, okay? Because it only has 1 vertex, okay? Yeah.
So if it's going flat at any point, that doesn't count as like a turning point?
No, because if it's going flat like that, it's still increasing. It doesn't switch to going down. Even if it goes 0, it doesn't switch to become going down, so it doesn't count as a turning point. That's a good question. Anyone else? Anything else? Okay, now, the other thing I want to bring up while we're on this page is that what was my A on number 1? Nope. 1. Remember, A is the number in front that shows if it's concave up or concave down and what its rate of change is, right? When A is 1, for a quadratic, that means it's concave up, right? What happens when A is -1 for a quadratic? Concave down. And it doesn't matter what other numbers are in there, right? It's just flipping if it's up or down. What we're going to notice is that we're going to be able to use that idea with higher level degrees also, okay? So on this one here, this is a cubic because there's 3 x's. So if I did put that into standard form, I'd have an x cubed. Does that make sense? What would the number in front, the A, be if I was going to do that? If I were to multiply that whole thing out, what would my A become?
Two.
Where are you getting 2?
Random guess.
Well, I appreciate the effort, but that is incorrect. It would still be 1. X times x times x, there's no coefficient in front of any of those, right? So wouldn't it still be +1? Okay. So this represents a positive cubic, just like this represents a positive quadratic. So I need you to keep that in mind. Okay? If I were to multiply this out all the way, what would its highest exponent be? Nope. 4. X cubed times another x. Only one person says, uh-huh. This back middle area, you need to give me some more feedback or I don't know what to do. Well, okay, but you gotta do the math. Do you wanna stand up? I'll get you a clipboard. Okay, so why is that an x to the 4th? Because you're multiplying the x's, and there's 3 x's represented here, because this is like x minus 2 times x minus 2 times x minus 2 and x plus 4, right? So if I were to multiply it out, that would be x to the 4th, right? What would the a be? The leading coefficient, what would the a be? It'd be 1. So if I were to multiply this whole thing out, I'd have a 1x to the 4th, right? So this represents a positive 4th degree.
Okay.
We doing okay?
Yep.
But I can't necessarily call that concave up and down because look, can you see how even though this is a positive cubic, it has parts that are concave down and parts that are concave up, right? So we got to think about it differently, okay? How are we doing? Acknowledge you're alive. Thank you. Okay, one more thing that until we start getting a bunch of information is we're going to learn a new concept called end behavior, okay? So the idea of end behavior tells me what is the graph doing as I go to the left and to the right, okay? So it's like another way to think about maybe domain and range or concave up and concave down. But the reason it's useful is because when you guys did quadratics, we could just say concave up and concave down because quadratics are always only one or the other, right? But in these higher level polynomials, sometimes I have parts that are concave down and parts that are concave up, okay? So here's how what we say is end behavior, okay? The notation is going to look like this. I'd say as x goes to negative infinity, I'm going to write it down here so I can write bigger. As x goes to negative infinity, y goes to this. As x goes to infinity, y goes to this. So this is like how the question would look, and we're going to fill in the blank. You guys seen this before?
Yeah.
Oh, great. I didn't know Sec 2 did this. Great. So as x goes to the left, negative infinity, on this positive quadratic, what's the y doing?
Infinity.
Y infinity. Someone else tell me y infinity. Y infinity. Someone else tell me y infinity. Because it's going up. Great. What about as x goes to the right? As x goes to the right, so positive infinity, what's the y doing? Still going up. Okay, let's try end behavior. Here. As x goes to negative infinity, And as x goes to infinity, yeah,
As x goes to negative infinity, y goes to negative infinity.
good, because as I go to the left, my graph's going down. And what about the other one? I want someone new. Yeah,
Normal infinity.
you got it. So the idea of the A when it's positive or negative is actually going to affect our end behavior now, not concave up, concave down, because the only polynomial that's only ever concave up or only ever concave down is a quadratic, and we're dealing with x cubes, x to the fourths, and things like that, okay? Let's try one more, and then we're going to start figuring out a bunch of patterns based on these things we've reviewed and learned on this page. So take a second and try it. Okay, so I got infinity for both. Okay, now hold on. Here's our pattern phase. Do you guys still have this one typed into your graphing calculators? Well, can you type it in real quick? But I want you to put a negative in front of the whole thing. Yeah, for a ticket. I already let you leave without one. So I want you to do it again, but I want you to put a negative in front of the whole thing. Doesn't it look like the same thing but flipped?
Yeah.
Okay, so here I want you guys to see if you can come up with our first pattern, okay? Can you look at number 1 and number 3 and tell me something that they have in common? Tell me something number 1 and number 3 have in common. I want that. Today's a pattern finding day. What's something they have in common? Here.
They both of their y and results go to positive infinity.
Both of their y results go to positive infinity. Until I switched this one and made it negative, right? But then now both of their y results for end behavior go to negative infinity. Okay, let's build on that. Here.
Kind of related to that, it still has one vertex.
They still have one vertex. That's good. Very good. Here.
Can you still classify it as having concave up? Because of its only one vertex, it's still.
That's a good guess. It actually, even though it doesn't, it only has one vertex, it's kind of tricky to see here, but there is a portion of that graph that's concave down where I highlighted red there, but that's a really good guess. Okay. What else? What else? Think about A.
I have to take a test. Is that okay if I
Yeah.
do that?
Mhm.
Thank you.
What about A? Here and then here.
So the a value determine like what the y value is going to be for the like the x as x goes to.
Absolutely. The A value, no matter the highest exponent, will always determine the end behavior. Always. Always. Because the A value is going to tell me where my arrows are pointing up or down, right? Okay? Was that what you were going to say, or do you want to add something else?
I was just gonna say basically the same thing, except the way I was gonna put it was that for at least before we flipped the graph, they both had an A of 1.
So before we flipped the graph on this one, they both had an A of 1, and both, the keyword in this one is both, went up, right? So what if I put a negative in front of both of them? Then what would happen? They'd both go down. Okay, so I know the exponent on number 3 is a 4, and the exponent on number 1 is a 2. What do those numbers have in common?
Even.
They are even. They're positive 2, that's good, and they're even. Okay, here's our first big pattern. Even degree, hold on, what's the word degree mean? The word degree? You guys have been talking about degree for years. Come on. Here.
What the exponent is?
The biggest exponent. Degree. Biggest exponent, right? If the degree is even, my end behaviors will go in the same direction. Always. Right? And what direction is that going to be if my A is positive? Up, up. And what's that direction going to be if my A is negative?
Down.
Down, down. Okay? You guys are doing great. Let's start putting some of this together more formally. So you